Okay, so I have a basic question to ask all of you. What are we? Like, what are we physically made of? Well, you may have learned that we are solid matter, and solid matter is made up of atoms, and an atom is made up of a nucleus, which is made up of protons, neutrons, and you have the electrons surrounding it. So that is half correct. So what I'm trying to focus in on is that matter is not just a solid substance, it is also a wave substance. So, I was fascinated by this when I took physics here at Fullerton College with Professor Kroll. He really opened up my eyes to this area of subject, and I want to try to expose you guys to this too. So hopefully you guys can appreciate this as much as I did. So yeah, and the reason matter is everywhere. It's everything, and you deal with it all the time. It's the whole universe. So if you learn this, you can have a better sense of reality, like what is going on in the world, you know. And okay, so my main points today would be I would introduce the properties of a particle and of a wave, because my statement was that matter is both a particle and a wave. And I would introduce the double slit experiment, which proves that matter is both a particle and a wave, and I would explain why it behaves this way. Alright, so my first point is the properties of waves and particles are fundamentally different, but they're not contradictory of each other. That means that they can coexist, so matter can both be a particle and a wave. I looked into my textbook, my physics textbook, for this information. My professor, Dr. Kroll, he wrote the textbook, The Modern Revolution in Physics, and I cited this information. So the property of particles, they are, first off, they are solid matter, and they only exist in whole numbers. That means you cannot have a partial piece of particle. So if you break up a particle, it's not a particle anymore. And then waves, the properties of waves, they are superimposable. That means that you can add them up together. So here you have waves, and you can have constructive or destructive interference. As you can see, constructive interference is when the peaks and the valleys of the waves, they line up with each other. See how right here the peaks and peaks line up and valleys line up? And what this does, it adds up the waves, so it becomes larger. You have constructive interference. Destructive interference is when the peaks lines up with the valley, and vice versa. And so you get a straight line because they cancel each other out. Alright, so that's the property of a wave. Okay, so now I'm going to introduce the double slit experiment. So basically the overview of this experiment is you take electrons and you fire it at a double slit, and this proves that electrons are, which is matter, are particles and waves. So I used this video on YouTube, Dr. Quantum's YouTube video. He just goes over the basics of the experiment. First, you got to focus on what would happen when you fire electrons at a single slit. A single slit is just like a piece of metal, and it's a very tiny slit. So what happens is, just imagine tennis balls. You're firing tennis balls at this slit, and you're gonna get an impression, or imagine they're paintballs. You're gonna get this single block on the other side, and that's the impression of where it's hitting and going through. So what happens when when a wave goes through the single slit? So when a wave goes through the single slit, you'll get a more focused wave, which is like the intensity is more, it's greater in the center right here. And when you see on the wall, go to the next slide. When you go see on the wall, all right, well, just go back. You will see like a single slab of like, you know, of where it's hitting, which would be right here, if you can imagine that. And okay, so that's what happens with a single slit. Now we're going to go into the quantum world and look what happens when you fire waves at a double slit. So in a double slit, you have two waves, and they're going to interfere with each other. See, you have the black lines and the white lines. So where the black and black lines meet, that's where you have constructive interference, and where the black and white lines happen, that's where you have destructive interference. So here's a 3D model of a double slit wave. As you can see, there's the impression on the back wall. You're going to have an interference pattern, which is, you see the lines, and that's where the energy is focused, because that's where the waves add up in constructive interference. And where the shadow areas are, that's where you have destructive interference. Okay. Okay, this is shining a laser, which is a wave, and you get a diffraction pattern like that. And okay, so now we're going to talk about, this is the final thing, we're going to talk about electrons through a double slit, which is, you're going to get an interference pattern too. This is not what you expect, because you expect electrons are particles, right? And you're going to have like two slits, so you're going to have two shadows on the other side. But you don't get two shadows. You get an interference pattern. So what does this mean? This means that it's a wave as well. So that's the whole thing. Electrons are also waves. Alright, so I'm going to kind of explain what happens, because this whole thing was a real mystery when scientists found out, because this is not what you expect out of a particle. First you have the uncertainty principle, which states that you cannot know exactly the momentum and the position of the electron at the same time. So when you're observing it, you can't find out which slit it actually goes through, because once you observe it, the particle, the electron, will go back to behaving like a particle. So you can't really tell which slit it goes through. So it goes through both slits. And so you just learned a basic concept of quantum physics, so you can take that to the bank, you know. Alright, and I hope you learned something and your mind is all blown, that you know now the electrons are particles and waves.
All right, Wes, what did you think?
I thought his attention device was good, but could have been developed more. And the introduction of his credibility was good. You know, he's taken the class, so he knows what he's talking about. I thought the signposting was good, but when he actually introduced the topics, I thought it could have been more conversation-like. The explanation itself was understandable, but I would have preferred if it related to more intuitive examples like marbles and maybe waves and water for people that aren't, you know, familiar with it. I am, so it's easier for me, but I don't know how others would relate to it. But overall, it was a good speech, I thought.
All right, I'd mirror most of your comments. The opening was fine. You identified the topic very clearly. I think you did a good job creating a justification and setting up the structure of the speech, so those things are solid. But the explanations, I think, remain kind of at an abstract level. This is something that might make sense in the context of a discussion in the physics class, but in a general audience where we haven't had that background, we're not sure why this is important and not so much controversial, but why it runs counterintuitive to our expectations. I don't know that anybody in here had any expectations about it. It's like you did a little bit to try and create this reason why we would see it one way at the beginning of the speech, but it wasn't a very clear example for us. And I kind of have to agree with Wes. I think you needed some more concrete, practical illustrations so that the general audience here would be able to appreciate it. This might be something that would work really well in your class if you were explaining it after you'd had a discussion in class about particles and waves and how they operate and how they really both are part of matter. Then maybe as a follow-up presentation this would work really well. But in the context of a general audience, I just feel a little bit like I'm not sure that I got what I needed out of this. And when you got to one spot where I thought there was the start of something that seemed a little bit more practical and concrete to understand. You had that 3D image that you were showing us, you know, the replication there, and I thought, okay, there's something that, but you talked about it very briefly, and then it was gone, and then we were on to the next thing, and I'm just going, okay, I'm not, and the whole thing with the slit, the double slit, I'm going, okay, now, there's a reason that these things matter, but we don't know what the reasons are, and I think that's part of the problem. But your descriptions of the interference and the way they intersected, I thought it was pretty, that was pretty clear. I just think that you need to do more to give it context-useful, you know, audience-friendly examples. And as a consequence, it's not quite as successful as you might want it to be. Although you do a nice job talking to the audience, and I'd agree with Wes that it's well organized. You did seem like you jumped ahead a couple of times on the visuals and then had to go back and forth, but that wasn't a big deal. I think you just realized that you needed to clarify something as you were speaking, and there were more things that needed to be clarified. All right, thank you.